Let's talk about polynomial curve fitting. In machine learning terms, this is a regression problem where we predict continuous numerical values. And in this video, we'll also tackle a critical issue, overfitting, where our curve gets too clever for its own good. So let's go ahead and generate our synthetic data set. So you can see the yellow portion. The first part is how we generate a clear sine wave, and the second part of the highlighted portion is how we add the noise. And here are our noisy observations. So our goal is to get our polynomial fit to match this true underlying sine wave, which is in blue, but not to hit every noise point. The tool we'll use is a polynomial function. So at its simplest, this is just y equals to w0 plus w1x, but we can add more terms like w2 x squared plus w3 x cubed plus to whatever degree m we choose. So we find the best coefficients w by minimizing an error function. So in this case, we are using the most popular error function, which is sum of the square errors. As shown in the screen, SSE, which is sum of square errors, simply measures how far your curve is from each data point, squares those distances to remove negatives, and sums them up. So we want the coefficients, which is w, in such a way that they make this sum, which is SSE, as small as possible. And now comes the million-dollar question, which is what degree m should we choose? So let's experiment. When m equals 0, we get just a horizontal line, and that's too simple. It completely misses the wave pattern, and this is a perfect example of underfitting. So next, when m equals 1, we get a straight line. That's still too rigid, and this is also considered as an underfitting case. So when m equals 3, now we are getting somewhere, right? So the cubic curve nicely captures the sine wave's shape without being too wiggly. But watch what happens when we get greedy. When m equals 9, there is a polynomial with 10 coefficients for our 10 data points. And this curve has zero error on our training data. It passes through every point exactly. But look how crazy it is between points. This is overfitting. It has memorized the noise, and this has not learned the pattern. So when a new point comes along, this wild curve will be completely wrong. So it fails a generalization. So how do we choose the right m? So we split our data, train on some, and test on some unseen data. Then we pick the m with the lowest test error. And the sweet spot is where the test error is minimized. And in our case, that's m equals 3. So that's the model that generalizes the best. So coming to this point, our big takeaways would be to not trust the training performance alone, and to know that the simplest model that fits well usually generalizes better, and overfitting is memorization, but we have to focus on